exactly like the graph that we saw last time that we explained. So what's happening is here I have static friction, and here is where the kinetic friction acts. And I want to just kind of say a couple more things about this graph. Again, kinetic friction means we're moving, static friction means that we're at rest, and throughout this whole region of kinetic friction, the formula for friction is fun. I want to be clear on one thing for static friction though. Here we always have, and in this case too, friction force always equals the pushing force in these free body diagrams, but what I want to be clear on is right here the maximum possible static friction happens at static friction equals mu static times the normal force. Until then, the friction goes from 0, and then I push harder, and friction goes bigger and bigger and bigger, and then I reach a maximum point of mu static times the normal force, and then it breaks, and then it starts moving. So what we can say here is that friction climbs up, so friction goes up until we get the max at mu static times n, then it starts moving. So you want to have all of that in your explanation. Now for question number 3, we've got a number of details here. So we have 50 kilograms metal block resting on ice. We want to know the maximum force that we can push it before the block starts moving. So this is going to be static friction. So I'm going to have static friction force equals coefficient of static friction times the normal force. So in this case, we know that the normal force happens to balance the weight. So Fg equals mg, which is going to be equal to our normal force because they balance. And so let's actually read this off here. So we have metal on ice, and the static coefficient is 0.022. So I can take 0.022 times the normal force, which I get from down here, and when I actually work all that out, my static friction is going to work out to 10.8 newtons